So you know that we've been talking about how to do systems of equations, right? So you have two equations, we want to find the solution. One of the techniques, the main technique I've showed you so far is how to use substitution to do it. Now, I didn't mention it, but there is another technique that usually comes before even trying to solve it by hand, and that's graphing. There is a way to graph both equations on the same plane. You know how to graph equations that are linear. You just plot 2 points, or you plug in an x, you find a y, plug in another x, find the y, plot those 2 points and draw the line between them. Okay, we've done that before. If you do that for both equations, you'll see where they intersect, and if you can find where they intersect, that's the solution. The problem with graphing is that you don't usually know very accurately where they intersect. It all depends on how well you can draw, right? Even if you draw on a computer, sometimes you can't tell exactly where they intersect, because what if they intersected like 4.3265, comma 3.21986, right? You get decimal numbers and they're not exactly on a nice whole number. You can't tell, okay? And so there's no reason why we couldn't get that. So we like solving using algebra, analytic techniques. What I'm going to do today is introduce you to a new technique. So if I had something like 4x plus y equals 5, and maybe 3x minus y equals 2. I'm already in danger of making problems up off the top of my head that I could get messy answers. But if I use the technique that I taught you last time, you could take one of these, for example, and take this 4x, move to the other side, right, and get y equals 5 minus 4x. Plug that into the y right here, solve that for x, and then back substitute, right? Yeah. I went through that pretty fast, but you remember doing that technique. It's just substitution. Okay, what I'm going to show you today is there are times where an alternate approach is actually going to be a whole lot faster than that. In fact, the way I wrote this problem, I gave you one where this works very, very well. Just imagine that I ask you to add these two equations up. Okay? If the first equation is true, the second equation is true, then if I add up this side, I should get the same thing as if I add this side up, right? So add straight up and down and see what happens. What's 4x plus 3x? What's y minus y? It cancels, and that's the key. Okay? When it cancels out, notice what you're left with in your final equation. How many unknowns do you have in this new equation down here? Just the x, right? Can you solve that for x? Divide by 7, you get x equals 1. Then if I wanted to solve for y, I could take that, plug it back into either one of these to solve for y. Okay? So the trick is, if I can add these two things up and one of my variables completely cancels out, then I've got an equation that has one equation with one unknown. Okay? What if they don't have that property? What if it's like 4x plus 2y equals 6? And what if it's 3x minus y equals 2? Notice in this case, if I add them up, I don't get rid of the variable, right? 7x plus y equals 8. Okay, no good. But I can get creative. Watch this. I'll erase what I just did. What if I took this system and rewrote it as 4x plus 2y equals 6, but take this equation right here and multiply it times 2. Just multiply both sides by 2. Okay? Now what happens over here if I multiply this by 2? 6x, and what if I multiply this one by 2? Minus 2y, and then this one by 2? equals 4. Now what happens when I add them up? 10x, the y's cancel, equals 10. I'm still able to cancel them out. So what I get to do now is think critically whenever I have one of these types of problems. If I want to cancel out one of my variables, I look for numbers that I can multiply one equation by, or maybe a different number for each equation, so that when I add them up, one of my variables cancels out. Okay? This method is known as the linear addition method. Okay? So if you go back to the title of the section, go back to the very beginning, we're going to solve systems using something called the addition method. So it's a completely new technique to solve systems, but it will get us the same answers as if we did substitution. And like I said last time, we're learning multiple techniques because sometimes one method's easier than the other, and sometimes the other method is easier. And this is the method that is easier for bigger systems. So depending on how far I get today, the end of this section has some 3x3 systems in this. So 3 equations, 3 unknowns. And the method we're going to use to solve that is this addition method. Okay, so if necessary, step 1 says to rewrite both equations in what's called standard form. ax plus by equals c. So on like this example down here that we're going to do in a second, that's going to be my first step, is I'm going to convert that into ax plus by equals c form. Like on those 2 examples that I did earlier, I had all the x's and y's on one side and all the numbers on the other. So like on this one, what that means to do is move the x's and y's so they're all on one side. So on this one, what would I move to get the x's and y's on one side? Add that y over to the other side, right? So plus y would give me 4x plus y equals 4. And what about the second one? Add the 3x. And I get 3x minus y equals 3. The reason why step 1 is so important is so that the x's, y's, and numbers line up. That'll make it easier to figure out which ones may cancel or what one we can multiply the numbers by so they do cancel. So if necessary, step 2 says multiply one or both equations by appropriate non-zero numbers so that the sum of the coefficients of the x's or the sum of the coefficients of the y adds to 0. So multiply one or both of the equations by something or some things so that one of the variables will cancel out when you add them up. Step 3, add them up. The result will be an equation with only one variable, right? That's what I've got here. You might underline that, or I'm going to highlight mine. The sum should be an equation with one variable. So then you solve that equation. Then we back substitute. Just like we did in substitution, once we know one of the variables, we plug it back into one of the original equations to solve for the other variable. And of course, like I've always said, 6, you can check the solution. You just plug it back into both of the original equations. So now that I've got down here this in standard form, we're looking for whether or not we can add them up and cancel out a variable, and if we can't, what can we multiply by so we can. Now in this case, what do you notice about the y's? They already cancel, okay? So all you got to do is jump to step 3 and add them up. 4x plus 3x, 4 plus 3, divide both sides by 7, x is equal to 1. Now I'm going to do that step that I call back substitute. Which means I've got to plug it back into one of the original equations. Now, there's no reason why you can't plug it into one of these right here, but it's safer to plug it into one of the original ones. And the reason I mean it's safer is because you could have made a mistake going from here to here, right? But you can plug it into one of these. Just plug it into an earlier equation. I'm going to plug it into this first one and solve for y. So 4 times 1 equals negative y plus 4. You see what I did? Just plugged in this x equals 1 into my first equation. Might have even been easier to plug it into my second one, but actually it is. I'm going to do the second one. So much easier. Look at that. Negative y. Somebody already wants to finish the one that we just did. You can double check that we get the same answer. Negative 3 times 1 plus 3. That gives me negative y equals negative 3 plus 3, 0, which means y is 0. So my solution is the point 1, 0. That's the point on both the lines. X equals 1, y equals 0 solves that system. All right, beautiful. Next one. I tell you what, this one's another pretty easy one, so why don't you guys go ahead and try solving this one on your own. I'm going to pause my recording, so if the guys watching the video pause now, they can try this one on their own as well. What did y'all get for your answer?
Negative 8, 15.
So what's your x?
3.
X is 3. Did y'all get 3?
Yes.
Okay, and then y was negative 8 over 15. Okay. Now the 3 is easy, right? Because when you add them up immediately, you get 2x equals 6. Divide both sides by 2, you get x equals 3. Piece of cake. Okay. We got high schoolers in town or on campus today for recruitment. Plainview High sent like 280 high schoolers over for different things going on today. I think Plainview is what's here today. I mean, we do different groups, but today's Plainview. Then you take that 3 and you plug it back into one of these, right? So if I do 4 times 3 plus 15 times y equals 4, that's 12 plus 15y equals 4. Subtract the 12, you get 15y equals negative 8. So divide by 15. That's where we get the negative 8/15. Okay? Yes, sir.
I did mine differently.
Okay, what was different?
Well, I moved,
Did you get this far? I mean, did you do this for the 3?
yes, but I moved the 4 to the left, and I moved the 15 to the other side.
Okay, so if you move the, I'm guessing we're to right here, we're the same, right? So you're saying subtract 4 from both sides and subtract 15y from both sides.
Yes.
Notice the minus goes with that 15 because you're subtracting it. So you get 8 equals negative 15y. So when you divide both sides by negative 15, it's still negative 8/15, right? The negative on top or bottom doesn't change. The whole fraction is now negative.
Oh,
So they're both right. Negative 8 over 15 is the same as 8 over negative 15. Right? That's the same as 8 over negative 15, which is the same as just putting a negative out front like that. Those are all three the same answer. Okay? Numerically, they mean the same thing. All right. Okay, so what if we throw you a little bit of a curveball and have the daunting task of handling big fractions or lots of fractions in your problem? Okay? Your first reaction is to clinch, right? You're like, ah, crap, fractions. It's going to be messy. I just don't. It's not like you're necessarily afraid of them, but you know it's going to complicate things, right? Like when you walk into a job and there's a lot of work piled on your desk that wasn't there the day before. You're like, oh, that means I've got some work to do. You know your job, you're good at it, but you still know there's going to be some work to do. But remember, I've taught you to think of homework problems as going to battle, and this, you have a secret weapon against fractions, right? Let's use that same secret weapon that I introduced to you way back when, the common denominator. If I multiply both sides of an equation by a common denominator, the fractions disappear. So what I would suggest, anytime you see a problem with a bunch of fractions in it, just get rid of the fractions by multiplying through by the common denominator. Like this first equation has a denominator of 5 and a denominator of 2. What's the lowest common denominator of those two? 10. So multiply the equation by 10. So if I take this number right here, 1/5 x times 10, what is 10 times a fifth? It's 10 on top and a 5 on bottom. 10 divided by 5 is 2. So the first term you get is 2x. What happens when you multiply 10 times 1/2 y? 5y. And what happens when you multiply 10 times 4? 40. That's an equivalent equation with no fractions. All right, what would you multiply the second one by to get rid of its fractions? You got a 3, you got a 3, so multiply by, okay, so times 3. If I multiply this first thing times 3, you have 3 on top, a 3 on bottom, so you're left with 2x, because they cancel, right? If you take the second one times 3, you have a minus 3y. And if you take the right-hand side times 3, you get what's 3 times 8/3. Same thing happens on this one that happened on the first one.
Equals 8.
3's cancel. 3's cancel. You're left with equals 8. Okay. Now, take a step back and look at this new guy. This equation, this new system, I can start ignoring the first one, and now we're going to solve this one instead. Now, if I add straight up and down, do any of my variables cancel?
Nope.
4x, 2y, 48. I still have two variables, okay? So the question is, can I multiply one equation or both by something so that when I do add them, they cancel? Right? I can, right? Just think of this is exactly the same as this, only if I change the sign, that it would work, right? So that's what I'm going to do. Go straight across, keep this the same. 2x plus 5y equals 40. And take the second one and multiply by -1. So what happens if I multiply everything in the second equation by -1? The x's will cancel. So tell me what the new equation looks like before I actually cancel them. -2x plus 3y, because it changed that sign, equals -8. It changes the sign of all three of them. Now, when I add, The 2x minus 2x is gone. I get 5y plus 3y, which is 8y equals 32. Divide both sides by 8. Y is faux. And what do we do with the faux? Plug it in. So we do back substitute. Okay, so I could plug it back into the original. I talked about plugging back into the original as a good strategy, but the thing I don't like about the original in this case is fractions. So I'm going to choose one of these two. It doesn't matter which one. So let's plug it in to say this first one. So you get 2x plus 5 times 4 equals 40. Now, again, if you ask me which equation to choose for back substitution, for the most part, it doesn't matter. One of your previous equations, okay? Assuming you did everything correctly, it doesn't matter which one you use. Sometimes that's a generous assumption. All right, so subtract 20 from both sides. 2x equals 20. Divide both sides by 2. X is 10. Which means my solution is 4, 10. Nope. 10, 4. Good buddy. 10, 4. Good buddy. Are we good? All right. So, if the fractions show up in the original problem, get rid of them first, then tackle the question of what can I multiply by so that one of my variables will cancel out when I add them. Okay, so on the next one, I'm going to get you started but let you finish. Let's look at this one where we got 10x minus 2y equals 6 minus 5x plus y equals minus 3. So we start with that equation. It's already in standard form, so the x's are lined up, the y's are lined up, the equals lined up, the right side is lined up. Okay. So which variable do you want to eliminate?
The y.
So you eliminate the y. Then you got to look at the minus 2y here and a plus y here. Which one can I multiply by something so they cancel? The second one by 2. That will work. That's not the only answer to the question, by the way. You very well could have chosen to cancel the x's. But let's do what you said. Which means the first equation I'm not changing. It's always good practice to just write it again right beside it. I like the little arrows next to it so I know exactly what I'm doing to the equation. So 10x minus 2y equals 6 stays the same. Second equation, what are you doing? Times 2. So that's minus 10x minus 2y equals minus 6, right? Plus 2y, you're right. Yep. You see what's going to happen? Add them up. What do you get? That's gone, right? That's gone. So if they both cancel, what are you left with? 10x minus 10x is 0, right? When you subtract something out, you get 0. Minus 2y plus 2y is 0. Equals 0. All right, when the variables are gone, you always ask, true or false? Is that a true statement that remains, or is it false? It's true. And if it's true, What does true tell you?
That 10, 0 already.
Okay, that was the answer when there was only one equation.
Oh, infinite answers.
Infinitely many solutions. It's dependent. So we can write infinitely
Looking for.
many solutions, or we could say dependent. Either one of those answers is correct. I said I was going to let you do it, but I just got too excited and I couldn't stop. I'm like a snowball, steamroller. No problem stands in my way.
So can you multiply both? By
Yes, so you can do two different numbers. As long as you multiply both sides of an equation by a number, same on both sides of the single equation, and then you choose a different number for the second equation, yes, you can do that. Which is what we're going to have to do on this one, right? Because there's, on part C, there's nothing I can multiply just like by this first equation, at least not a whole number, I should say, or an integer, that will make it cancel, right? I couldn't multiply this by something. I can't multiply 2 by a whole number or an integer and get 3. I can't multiply 5 by something and get 4. I can't multiply, well, I don't even care about the right-hand side. And vice versa. I can't multiply 4 by a whole number and get 5, or even a negative 5, and so forth. So what I'm going to do is I'm going to come up with multiplying both of them by something. So think of like the x's. What can I get 2 from 2x and negative 3x?
Times 3 and then multiply in the bottom one by 2.
Yep. That both gets me to 6x, right? A 6x on top and a minus 6x on bottom. So if I multiply this one by 3 and this one by 2, then I will have 6x plus 15y equals 16 times 3 is 48. And if I take the second one times 2, I get a minus 6x plus 8y equals negative 2. See how I just multiplied everything by 2. Now add. Six x is gone. 15 plus 8 is 23y equals 46. Divide both sides by 23. Y is 2.
what did you say?
Now back substitute.
What did you say?
Are we okay with the 2? Everybody get there?
Yes.
Okay, so plug the 2 back into one of these y's. I'm going to use the first equation. So 2x plus 5 times 2 equals 16. So that's 10. So I move to the other side. I get 2x equals 6, which means x is 3. So my answer is 3, comma 2. So this is where it can get challenging, is if you don't see immediately what you can multiply them to, just realize, or multiply both of them by something different. Realize that it's actually the same question as finding a least common multiple or lowest common denominator of those two coefficients, right? Like up here, when I had a -2 and a 1, the LCD of 2 and 1 is 2. So I knew I needed to get this one up to a 2, so I multiplied by 2. If you look at 2 and -3, the LCM, or the LCD, the lowest common denominator, smallest number that both 2 and 3 go into is 6. So I've got to multiply 2 by something to get to 6. That's the 3. I've got to multiply 3 by something to get to 6. That's this 2. So that's one way to help figure out what you have to multiply by so that they cancel. But after that, the process is the same. The next page in your notes is just a quick summary of some of the information that I've given you to compare the different solution methods. I mentioned earlier this graphing technique and said graphing is good in the sense that you can do it, you can see the solutions, but it's bad because it's hard to tell, in fact it's impossible in many cases, to tell exactly what the solutions are from looking at the graph. That means just graph the two lines and see where they intersect. It's very hard to solve that way exactly. So we have two methods that we prefer, either substitution or addition. Substitution is best if the variable is easy to solve for one side by itself. So if you go back to the examples that I did in 9.1, they were all very easy to solve for one of the variables. In fact, the only ones we did was where one of the variables had a coefficient of 1. Now if I backed up a slide and looked at this problem right down here, I would not want to solve this one by substitution. I wouldn't want to solve, say, this first equation for x or for y, because that creates fractions, and you can't get rid of them. So, the advantage is substitution is nice if it's easy to solve for a variable on one side by itself. Disadvantage, solutions can't be seen visually from looking at it, and it's got extensive work with fractions when no variable has a coefficient of 1 or -1. Addition is a good method because it gives exact solutions, and it's easy to use when you don't have a coefficient of 1 or -1. Actually, it's easy to use even in that case. They only list one disadvantage. I would write an additional advantage. An additional disadvantage is in some cases it's more work by hand to use this technique. I'm not going to write it down because that's not always the case. So I would say when substitution is easy, use it. Otherwise, use addition. Note, it's extremely helpful to understand these relationships as well as any other relationship between an equation and its graph. That's these down here. Just remember, one more time, that you have 3 different types of answers that you can get for a system. You can get exactly one solution. Do you remember what we call it when we have exactly one solution? Flip back to 9.1. I gave you names. There's 3 words for these. Independent. What about when it has no solution? We have another, there's a single word for it. Close. Where did I write it up?
Inconsistent.
Very first page.
Inconsistent.
Inconsistent. Notice, by the way, you know it's one solution if you get an answer using our techniques, if you get a single answer. You know it's no solution if your variables cancel out and you end up with a false statement. And if you end up with a true statement, we say it has infinitely many solutions, which is dependent. So you have two techniques for solving 2 by 2 systems now: substitution and addition. Now, both of those techniques can actually be generalized to 3 by 3 systems. So let's talk a little bit about what we mean when we call a system a 3 by 3 system. An equation that has a third variable. Now, I've introduced another variable. We're going to call it z. ax plus by plus cz equals d, where a, b, and c are coefficients of the variables, d is a constant. This is called a linear equation in 3 variables. Okay, now when you graph an equation that has 2 variables, you get a curve, okay? And if you graph a linear equation, you get a straight line, right? If you have 3 variables, you no longer graph on a plane, not on a flat surface like the chalkboard. You graph in space, in 3 dimensions, okay? A linear equation in 3 dimensions is a plane. Not an airplane, like plane, like flat plane. It's a flat surface. Take a piece of paper and imagine that it's completely flat, oriented some direction. Poor guys on the video can't see me waving paper at you guys, but they can have to use their imagination. Dr. Franklin with his flat paper, and it extends infinitely out in any direction. Okay? So that's a plane. Now, if you have 3 of those, and they all are going different directions, most of the time they'll intersect at a single point. Okay? The solution of an equation is that point which has 3 coordinates. It's called an ordered triple and looks like this: x, comma, y, comma, z. And it's such that it solves all 3 equations. So each equation. All right, so I'm going to draw a picture off to the side here just to kind of give you an idea. If I had, let's say I have a plane. You don't have to draw this unless you want to try. Going this way. There's one plane. Say I've got another plane going this way. So it intersects along this line right here. Okay? Now I'm going to draw a third plane that's up and down going this way. Okay? So it intersects this one along here and intersects this one along here. So in this picture, notice you've got a plane that's flat, the red one, a plane that's kind of up and down coming out towards us, and a plane that is right there on the screen itself, flat with the screen. Okay? That point inside there is the only point that's on all 3 of those graphs, of those planes. Does that make sense?
Which one is the blue?
So the red one is flat, the purple one's coming out towards us, and the blue one here is flat against the screen. So this one's like the ground. The red one's the parallel to the ground this way. So there's only one point that's on all 3 of those planes at the same time. That's the one in the middle. Okay? So if each of these were to be graphed, they might look something like this. There's one point that is on all 3 of those. I ask you on this one to show that the ordered triple is a solution. So this was just extra. You wouldn't do this on your homework, right? This is just to help you visualize what's going on. But if I ask you to verify or show that a triple like this one is a solution, that means it has to satisfy all 3 of those equations at the same time. So to verify that, what I do is plug it in. So I let this first variable be x. So x is 2. Y is going to be -1, and z is going to be 3. So let's plug it in and see what we get. 2 plus a -1 plus a 3. Is that equal to 4? And it is, right? Because 2 minus 1 is 1, 1 plus 3 is 4 equals 4. Okay, what about the second one? X is 2 minus 2 times negative 1 minus z, which is 3. Is that equal to 1? So that's 2 plus 2 minus 3. That equals 1, so yes, that works. Right? Because 4 minus 3 is 1. So let's do the last one. 2 times 2, my x is 2, minus a minus 1 for y, minus 2 times 3 for z. See, what I'm doing is, again, plugging in x equals 2, y equals negative 1, and z equals 3. So on the left-hand side, I get 2 times 2, minus a minus 1, minus 2 times 3. Is that equal to negative 1? Okay, so that's 4 plus 1 minus 6. So that's 5 minus 6, which is negative 1. Check. So the answer to this question is yes, it is a solution. But you have to show it, and that's what we just did. Now I'm out of time, but the next obvious question is, instead of me giving you the solution to the system and you checking it, can I just give you a system and you find the solution? So we want to solve systems in 3 variables by eliminating the variables. We got time to fill in the blanks, but we don't have time to do the example. So let's fill in these blanks, and next time we'll come in and do an example, okay? So what you do, basically the technique is to reduce the system to 2 equations with 2 variables. We turn a 3 by 3 into a 2 by 2. On this next example, what that means is I figure out a way to add 2 equations together to eliminate one of the variables. Like I would add the first 2 equations together, and that would eliminate my z. Okay? So that gives me 1 equation with 2 unknowns. My second step is to try a different pair of equations than the first 2. Try any other pair, the first and third or the second and third, and eliminate the same variable again. I eliminated z the first time, take a different pair of equations and eliminate z again. That results with now 2 equations with 2 unknowns. I've reduced my system from 3 variables down to 2 variables with 2 equations. Again, we'll walk through this in class on Monday. You solve that resulting system. You then back substitute to get your last variable. You plug it all back into the original equation to make sure you've got the final set of answers. And then you check the proposed solution in all the original equations. Again, that check step is the one that I leave out occasionally in class. All right, I'm going to stop there, and we'll come back next time, and we'll do a couple of these 3 by 3 systems. Okay?
Yay.
I know you can't wait. But the homework that I've assigned, since I didn't finish, I think it says it's due Monday, but you'll have extra time. We have class on Monday. That's the only time we meet next week because of Thanksgiving. So the next homework won't actually be due until the following Monday after that. All right, I'm done.